Let's look at another outflow boundary case that impacted a fire. We'll focus on the late afternoon to evening hours of June 30, 2025, and focus on the Oak Ridge Fire in eastern Arizona. This 4-panel display of GOES imagery shows the natural color RGB in the upper left panel, the 3.9 micron imagery in the upper right panel, the fire temperature RGB in the lower left panel, and the IR band at 10.3 microns in the lower right panel. First, let's identify the Oak Ridge Fire being associated with the hotspot located here. The hotspot appears intermittently since there are convective clouds which cause obscuration at times. Early in the loop, we observed convection in western New Mexico. This led to the development of an outflow boundary that was approximately north to south oriented and moved westwards into Arizona. I'll stop the loop to annotate the outflow boundary. Here's the location of the outflow boundary in the natural color RGB at that time. Winds were strong just behind the outflow boundary, which caused rapid fire spread, as can be seen with a pyrocumulus burst in the natural color RGB and an increase in magnitude of the hotspot temperature as detected in the 3.9 micron band. Let's go ahead and focus in on that pyrocumulus burst. So if we go ahead and focus in on this region, we can see a pyrocumulus burst right here. There's the outflow boundary. So we have strong winds immediately behind the outflow boundary, and that helped to cause rapid fire spread. And associated with that, this pyrocumulus burst. And also we saw a flare up in the 3.9 micron brightness temperatures. Next, we'll consider the radar perspective of this outflow boundary. Before we show output from radar, let's look at the MRMS radar quality index from the nearest radars. To the west, we have the radar in Flagstaff, Arizona, and to the east, we have the radar in Albuquerque, New Mexico. The location of the Oak Ridge Fire is right here, which is far from either radar site, resulting in low radar quality index values. Keep this in mind as we look at data from each radar site. We'll start with data from the radar site in Albuquerque, since this is closer to where the outflow boundary originated. All radar data shown here is from the half-degree tilt, reflectivity in the upper left panel, velocity in the upper right panel, correlation coefficient in the lower left panel, and GOES natural color RGB in the lower right panel for comparison purposes. Early in the loop, we can see the convection in the reflectivity field that led to the outflow boundary. Indications of the outflow boundary begin to appear near the end of the animation in the vicinity of the Arizona-New Mexico state border, but is subtle, especially when compared to the natural color satellite imagery. Keep in mind the outflow boundary is moving away from the radar in time, making it less likely to be detected. We switch to the Flagstaff, Arizona radar, looking at the same fields, which depicts the outflow boundary in the later part of this animation. In this situation, the outflow boundary gets closer to the radar site in time, making it more likely to be detected. This case illustrates the challenge of detecting outflow boundaries by radar due to significant range from the nearest radar site, a typical issue in the western U.S. Be sure to use satellite and surface observations in tandem with radar observations for the best possible detection of outflow boundaries that can impact firefighting operations.